I earned my degree online at Arizona State University. I chose to get my degree at ASU because I knew that I'd get a quality education, they were recognized for excellence, and that I would be prepared for the workforce upon graduating. To be associated with ASU, both as a student and alum, it makes me extremely proud, and having experienced the program, I know now that I'm set up for success. Learn more at asuonline.asu.edu.
Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. Twis week in astronomy. Dark energy might be changing. Hidden star orbiting Betelgeuse and first glimpse of rocky planets forming. Dark energy might be changing over time. Around 1998, scientists made a discovery that completely changed how we understand the universe. They had been studying the light from about 50 exploding stars called Type Ia supernovae. These explosions happen when a certain kind of dead star, called a white dwarf, blows up in a very specific way. Scientists used them to try to measure how fast the universe was expanding. But what they found was shocking. Instead of slowing down or expanding steadily, the universe was actually speeding up. Something unknown was pushing it to expand faster and faster. That mysterious force was later called dark energy, and the discovery won a Nobel Prize. Since then, researchers have continued to observe these supernovae using different telescopes and methods. Over 2,000 of them have now been recorded. But because each experiment is slightly different, it's hard to compare the results directly, like trying to compare apples to oranges. To fix that, scientists created the biggest and most unified collection of Type Ia supernova data ever. This new set is called Union 3, built by an international group called the Supernova Cosmology Project, led by researchers at Berkeley Lab. By putting all these supernovae on the same measurement scale, scientists can now study dark energy with greater precision. The latest analysis suggests that dark energy might not be staying the same over time, it could be changing. That's a big deal. It's not yet a solid conclusion, but it does match what other studies are also beginning to suggest. One of those is the Dark Energy Spectroscopic Instrument, DESI, which studies the way galaxies group together. Another supernova study from the Dark Energy Survey seems to show the same pattern. Even though scientists are cautious and not jumping to conclusions, they're definitely paying attention. Two very different techniques are starting to show results that don't quite match what our current main theory, called the Lambda CDM model, predicts. This model assumes that dark energy has always had the same strength and that it pushes against gravity, which is mainly caused by something called dark matter. But now, some scientists think a model where dark energy changes over time might better match what the data shows. If that's true, it could completely change our understanding of how the universe works and even how it might end. Dark energy makes up about 70% of the universe, and it's the reason space is stretching apart. If it starts to weaken, that could mean the universe might one day stop expanding so quickly, or even slow down completely. It could even start to shrink again. That's why researchers are so eager to understand how dark energy behaves. To do that, they trace the history of the universe's expansion by looking at supernovae. Because these explosions always have the same brightness, scientists can use them like standard light bulbs to measure distance, like using identical candles to tell how far down a hallway something is. They also measure how much the light from each supernova shifts toward red, which tells them how much the universe has stretched since the explosion. Union 3 includes 2,087 supernovae from 24 different studies and lets scientists look back over about 7 billion years of space history. That's a huge upgrade from the older Union 2 dataset, which had only 557 supernovae. To put them all on the same scale, scientists looked closely at each supernova's brightness over time, how it gets bright, peaks, and fades. That lets them figure out the true brightness of each explosion and adjust for any differences, like recalibrating candles made by different brands. They also used a more advanced method to analyze the data, one that can deal better with uncertainties and incomplete information. This method is called a Bayesian hierarchical model, and it can handle things like small changes in telescope filters over time that might affect how much light was recorded. This makes the final results more accurate than before. In the near future, scientists plan to add even more data to Union 3, especially from supernovae that are closer to us and from those that happen much farther away. These additions will help refine the measurements even more. One scientist, Greg Aldering, said they wanted to establish a solid base before adding several hundred more nearby supernovae, because this is the area where calibrations are most sensitive and where they've had the weakest data so far. He believes their new method lets them understand the calibration better than anyone has before, and they're eager to see what more supernovae will reveal. Looking further ahead, even bigger collections of data are on the way. Over the next 10 years, powerful new telescopes like the Vera C. Rubin Observatory and NASA's Nancy Grace Roman Space Telescope are expected to capture tens or even hundreds of thousands of new supernovae. With the improved analysis method from Union 3, researchers will be ready to include all that data. To fully understand dark energy, scientists aren't relying on just one method. They also look at how galaxies form patterns, using a technique called baryon acoustic oscillations, or BAO. This method works better for studying the early universe, when dark energy wasn't as important yet. Supernovae, on the other hand, give very precise information about the more recent universe. Together, these two methods are finally becoming accurate enough to test different ideas about how dark energy behaves. The work is also a great example of how powerful scientific collaboration can be. At Berkeley Lab, scientists working on supernovae and others working on BAO shared insights and helped each other improve. They also combined these findings with measurements of the early universe's light, the cosmic microwave background, or CMB, to get an even clearer picture. All these pieces are coming together to help scientists understand what dark energy is, whether it changes over time, and what that means for the fate of the universe. Hidden star found orbiting Betelgeuse. Betelgeuse is one of the brightest stars we can see at night, and it's also the closest red supergiant to Earth. It's absolutely huge. Its radius is about 700 times that of the Sun. Even though it's only about 10 million years old, which is pretty young in space terms, it's already getting close to the end of its life. You can find Betelgeuse in the constellation Orion, where it forms one of the shoulders of the figure. People have been watching this star for thousands of years, and they noticed that its brightness changes over time. Scientists later figured out that Betelgeuse has two main brightness patterns, one that repeats roughly every 400 days, and another longer one that takes about 6 years. In 2019 and 2020, Betelgeuse suddenly got much dimmer, and many thought it was about to explode in a giant supernova. But it turned out that this great dimming happened because the star released a large cloud of dust that blocked some of its light from reaching us. That solved the mystery, but it made scientists much more curious about the star and inspired them to look at past data with fresh eyes. One idea that came up was that the long, 6-year pattern in Betelgeuse's brightness might be caused by another star orbiting around it, a companion star. Astronomers used powerful telescopes like the Hubble Space Telescope and the Chandra X-ray Observatory to look for this companion, but they couldn't find anything, until now. A team led by Steve Howell, a scientist at NASA, has finally found this companion star. They used a special camera called Allopeak, which is attached to a huge telescope in Hawaii called Gemini North. This camera uses a technique called speckle imaging, which takes super short snapshots to cancel out the blurring caused by Earth's atmosphere. With this method and the telescope's strong light-collecting power, they were able to actually see the faint companion star next to Betelgeuse. By studying the light from the companion, Howell's team could learn more about it. It's much dimmer than Betelgeuse, about 6 times dimmer in visible light, and it's likely a young, hot star that's still forming. It's around 1.5 times the mass of our Sun and hasn't even started burning hydrogen in its core yet. What's really impressive is how close this companion is to Betelgeuse. It's only about 4 times farther away than the distance between Earth and the Sun, which means it's orbiting inside the extended outer layers of Betelgeuse's atmosphere. This is the first time a star this close has been directly seen orbiting a supergiant like Betelgeuse, and it shows just how powerful and precise the Gemini telescope is when paired with Alippeek. This discovery helps scientists better understand what Betelgeuse's life looks like now and what will happen to it in the future. The two stars were likely born together, but the smaller companion star will have a shorter life. Over time, gravity will cause it to slowly spiral into Betelgeuse and eventually be destroyed, probably in the next 10,000 years. Finding this companion also helps explain why other red supergiants might change in brightness over long periods, something scientists have been curious about for a long time. Howell hopes that now that they've been able to detect such a faint and close companion, other similar discoveries might follow using the same method. Another scientist, Martin Still, says this result is a big win for the Gemini Observatory, showing what it can do for many types of space research. Solving the mystery around Betelgeuse that has lasted for hundreds of years is a major scientific achievement. The team plans to take more observations in 2027, when the companion star will be farthest away from Betelgeuse in its orbit and easier to spot again. They hope to learn even more during that time and continue uncovering the secrets of this famous star. First glimpse of rocky planets forming around baby star. Astronomers have managed to spot the very beginning of rocky planets forming around a young star that looks a lot like our Sun did long ago. This discovery gives scientists a rare and important look into what the very first stages of planet formation might have been like in our own solar system billions of years ago. For the first time, researchers have clearly seen the hot area around a baby star where rocky planets like Earth can start to form. This moment is like a time-zero snapshot, right when solid material first begins to appear. It's something scientists have been hoping to catch for a long time. To make this discovery, NASA's Webb Space Telescope worked together with a powerful set of telescopes in Chile known as the European Southern Observatory. They focused on a very young star called HOPS 315, located about 1,370 light-years from Earth. It's still in its early stages of life, only about 100,000 to 200,000 years old, but it's expected to become a star like our Sun. In space terms, that makes it practically a newborn. Because the star's disk of gas and dust is tilted just the right way, astronomers were able to see deep into it. They discovered tiny solid specks forming inside the hot gas, early signs of rocky material coming together, which is how planets begin. They also found materials like silicon monoxide gas and certain kinds of hot crystals, similar to the ones that scientists believe were the first solid things to form in our solar system, back when it was just beginning over 4.5 billion years ago. Before this, no one had ever directly seen this type of mineral formation happening around young stars. Scientists weren't sure if it was something that always happens when planets form or if our solar system had been an unusual case. Now, this new observation suggests that this process might be common in the universe. Other studies have looked at disks of gas and dust around young stars, and some have seen possible signs of planets forming later on. But until now, there hadn't been solid proof of that very first step, when dust starts becoming the building blocks of rocky planets. In a picture taken by the ALMA telescope network in Chile, this forming planetary system looks like a small light shining in the darkness, something delicate and just beginning. It's not yet clear how many planets might eventually form around HOPS 315. The gas disk surrounding the star is about as big as what our own sun may have had long ago, so it's possible this system could end up with several planets, maybe even 8 like ours, though that would take millions of years. One of the scientists involved, Merrill Van T. Hoff from Purdue University, hopes to study more young stars like this. By comparing them, astronomers might figure out if making Earth-like planets is something that happens all the time in the universe, or if Earth is a rare exception. This discovery gives hope that planets like ours could be forming in many places across the galaxy, and maybe even worlds that could one day support life.